Next question is state true and false. So first, minimize the number of arithmetic operations whenever possible. So that this statement is true. There are many reasons why it is beneficial to minimize the number of arithmetic operations whenever possible. First reason can be efficiency. Performing arithmetic operation is the computationally expensive process. By minimizing the number of operations required, we can improve the efficiency and reduce the processing time. Next benefit is accuracy. Each arithmetic operation introduces a certain degree of error which can accumulate over multiple operations. As number of operation increases, so increase. By minimizing the number of operations, we can reduce the overall error and improve the accuracy of the result. Next benefit is robustness. Arithmetic operation can also lead to numerical instability and divergence, especially when dealing with large or small values. By minimizing the operation, we can reduce the risk of numeric instability and make the algorithm more robust. Next benefit is memory usage. Each arithmetic operation requires storage in memory. By minimizing number of operations, we can reduce memory usage and optimize the use of available resources. So, hence, minimizing the number of arithmetic operations can lead to more efficient, accurate, and robust algorithm with lower memory requirement. So, first statement is absolutely true. Next, avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of the problem. If it cannot be avoided, take the difference before doing other operations. So this statement also seems true. Let's see how. Taking difference of two nearly equal number can lead to loss of accuracy and numeric instability, especially when dealing with floating point number. This is because the difference between two nearly equal numbers can result in a very small number that may be lost due to the limited precision of floating point arithmetic. To avoid this problem, it is recommended to use an alternate formulation of the problem that avoids taking the difference of two nearly equal numbers. This can involve al- this can this can involve algebraic manipulation or reordering the calculation to reduce the sensitivity to small change in the input. If it is not possible to avoid taking the difference of two nearly equal numbers, it is recommended to take the difference before performing the operation. This can help to reduce the impact of loss of precision and improve the accuracy of the result. Overall, avoiding the difference of two nearly equal numbers by taking difference before performing the operation can help to improve the accuracy and numeric stability of algorithm that involve floating point numbers. So the second statement is also true. Now next, adding or subtracting number when with adding or subtracting number starts with the smallest number and work with number in ascending order. Let's see it's true or false. Adding or subtracting number starting with the smallest number and working with number in ascending order can help to improve the accuracy and numeric stability of calculation. When adding or subtracting number with different magnitude, it is important to start with smallest number to reduce the impact of the limited precision of floating point arithmetic. This is because small numbers have very fewer digits and are less sensitive to rounding errors than large numbers. By working with number in ascending order, we can also reduce the accumulation of rounding errors and numeric instability. This is because rounding error accumulate more rapidly when adding or subtracting large numbers, while small numbers are less sensitive to these errors. Therefore, adding and subtracting numbers, starting with smallest number and working with number in ascending order can help to improve accuracy and numeric stability of calculation, especially when dealing with floating point arithmetic. So this statement is also true. Next, do not formulate an algorithm that tests whether a floating point number equals to 0. Let's see why. It is not recommended to formulate an algorithm that tests whether a floating point number equals 0 because floating point numbers are not exact and their value may be subject to rounding error. Due to the limited precision of floating point arithmetic, it is difficult to represent certain number exactly, including 0. This means that even if two floating point numbers are mathematically equal to 0, their representation in memory may differ due to rounding errors. Instead of testing whether a floating point number equals 0, it is better to use a threshold or tolerance value to check whether the absolute value of number is sufficiently small. This approach is also known as an epsilon test. Using an epsilon test, we can handle floating point number more accurately than testing the exact equality to 0. Therefore, this statement is also true. Next, preconditioning of problem is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way, if detect suspected ill conditioning, is to alter the parameter by small amount and observe their effect on the solution. Okay, so this statement doesn't seem true. Let's see how. Ill conditioning of problem can be due to improper formulation, but it can also be due to nature of problem itself. Ill conditioning means that small change in the input or parameter of problem can lead to large changes in the output or solution. This makes the problem difficult to solve accurately and can lead to numeric instability. One way to detect suspected ill conditioning is indeed to alter the parameter by small amount and observe their effect on the solution. This is known as sensitivity analysis. By analyzing the sensitivity of solution to changes in the input parameter, we can determine whether the problem is well conditioned or ill conditioned. If the solution is highly sensitive to small changes in input, then the problem is likely to be ill conditioned. However, simply altering the parameter by small amount may not always be enough to eliminate ill conditioning. In some cases, a careful reformulation of the problem may be necessary to improve its conditioning. This may involve changing the formulation of the problem, introducing additional constraint or assumption, or using different numeric method or algorithm. Therefore, while detecting suspected ill conditioning through sensitivity analysis is useful, is first step. Addressing ill conditioning may require a more thorough analysis and reformulation of problem. Therefore, this condition is partially true. Next, after a numerical algorithm is obtained, check if it can lead to a numeric instability. In such algorithm, errors grow in each step of calculation. In such case, reformulate the solution procedure to get a stable numeric algorithm. This statement also seems partially true. Same reason can be valid. Numeric algorithm can indeed lead to numeric instability, where error grow in each step of calculation. This can be due to variety of factors, such as ill conditioning of problem, numeric round of errors, or instability in the algorithm itself. To ensure numeric stability, it is important to carefully analyze the algorithm and its implementation to identify potential source of instability. This may involve testing of the algorithm on a range of input values, examining the behavior of the algorithm as the input values are varied, and comparing the result with analytic or exact solution where possible. If numeric instability is detected, then the solution procedure may need to be reformulated to get a stable numeric algorithm. This may involve using alternative numerical method or algorithm that are known to be more stable, modifying the existing algorithm to reduce the impact of numerical error or roundoff, or introducing additional constraint or assumption to improve the conditioning of the problem. Therefore, while checking for a numerical instability is an important step in the development of numerical algorithm, addressing instability may require a more thorough analysis and reformulation of the algorithm to ensure that it is stable and reliable for a range of input values and conditions. So, this statement is also partially true. Next, if severe rounding error and consequent loss of significant digits are anticipated and no alternate formulation to avoid this is possible, then carry more significant digit in the critical calculation using floating point number in double precision mode. In this mode, the length of mantissa is twice that of the other floating point quantities. This statement is true. Severe rounding error and consequent loss of significant digit can occur in numeric calculation, particularly when dealing with quantities that vary widely in magnitude or when performing operations on values that are close to the limit of machine precision. In such cases, if no alternate formulation is possible to avoid the loss of precision, carrying more significant digits in critical calculation can help to minimize the impact of rounding error. One way to achieve this is by using floating point number in double precision mode, which allow for twice the number of digits in the mantissa compared to the standard floating point number. This can help to increase the precision of critical calculation and reduce the potential for rounding error to affect the accuracy of final result. However, it is important to note that increasing the precision of calculation can also increase the computational cost and memory required of the algorithm. Therefore, it is important to carefully balance the need for precision against the computational resource available and consider alternative method of formulation where possible to reduce the impact of rounding error on the final result. Hence, this statement is true. Next, double precision require large memory save and slow down calculation. Very much true. We have seen now already. Double precision require more memory space than standard single precision, as each doubles the precision floating point number required. 64 bits of memory compared to 32 bits for single precision number. However, whether or not double precision slowdown calculation depends on the specific context and computational requirement of the algorithm. In some cases, double precision may be necessary to achieve the desired level of accuracy or to avoid numeric instability caused by rounding error. In these situations, the benefit of increased precision may outweigh the additional memory requirement and computational cost. In other cases, where lower precision is sufficient and where the computational resources available are limited, it may be more efficient to use single precision floating point numbers or to consider alternative method of formulation that reduce the impact of rounding error on final result. Ultimately, the choice of precision for numerical algorithms should be based on carefully consideration of the trade-off between accuracy, computational efficiency, and memory required, taking into the account the specific context and goal of the problem being solved. Hence, uh, um, This statement is true, but this is not that much true. It is partially true. Hence, the whole statement is partially true. Next, in third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method, relative error is 0.0013. So we need to solve this. Let's do this later. First, we discuss this question. The iterative method are compared on following parameters: the rate of convergence, the amount of computational effort per iteration, the sensitivity of the method to the starting value and immediate value. Yes, correct. The iterative method are commonly compared based on the following parameter: rate on convergence. It refers to how quickly the iterative method converges to the desired solution. The faster the rate of convergence, the better method. Amount of computational effort per iteration. It refers to amount of computation required to obtain the next approximation in the iterative process. A method that requires less computational effort per iteration is preferred. Next, sensitivity of the method to the starting value and the immediate value. This refers to how sensitive the method is to the initial guess and immediate guess used in the iterative process. A method that is less sensitive to the initial guess and immediate is preferred. Now let's discuss this ninth question. In third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method, relative error is 0.0013. To answer the question, we need information such as formula and the previous approximation obtained. However, based on the given information, we can make a guess. Assuming that the formula used to find the square root of 5 is x into n plus 1, which is equals to 0.5, which is x into xn plus 5 upon xn. So this formula is x n plus 1, which is equals to 0.5 xn plus xn plus 5 upon xn. Okay, where xn is the nth approximation and xn plus 1 is the n plus 1th approximation. We can estimate the value of x3 iterative third iteration as follow. So we can find x3 by x0 is 7 given the starting value. x1 using this formula we have find out 3.07143. x2 using this formula we have found out 2.23862. Now assuming the relative error is defined as, so the formula for relative error is this: x into n plus 1 minus xn divided by mod of x into n plus 1. Okay, we calculate the relative error between x2 and x3. Relative error is x3 minus x2 divided by x3, which is equals to 0.001. Solving for x3 in the above equation, we get x3 minus x2 is equals to 0.0013 into x3. Assuming that x3 is positive, we can simplify the equation as follows. x3 minus x2 is equals to 0.0013 into x3. Substituting the value of x3 and x2 we get. So we take x2 and x3 from above. So we get x3 minus 2.23862 is equals to 0.0013 into x3. On solving, we get x3 equals to 2.24119. Therefore, the third approximation of square root of 5 with Newton-Raphels method with starting point 7 and relative error 0 is approximately this. So we have found out the value. And what was the question? Okay, so that's all for this list of questions. Thank you.